say. Okay, let's go ahead and get going. Okay, so the formalities are, probably not great today, but I think more or less everyone knows one another, and quite a few people know even roughly what's going to be in this class. John spent a lot of time putting a website together, which I think most of you have already seen. He's got a lot of things ready. So I don't know if there's a lot I need to say. John's put a lot of work into making this class happen. And in a lot of ways, I'm going to be the same kind of student that you are for many things that we do. I guess roughly, obviously, to a lot of you, a lot of this stuff is involves things that I've had a lot of experience with, but especially because John's put things together in a different way, in a much more modern way. I'm going to be as much of a learner in many classes as you are. So, what else do we need for an introduction? How's that sound to you, Bob?
That sounds pretty good to me. I don't know that we need. Would it help if people said their name for the few people that don't know each other, or are we all pretty comfortable?
Know one another? Okay, let's blast around the room.
Yeah.
Emily, hi.
Yeah.
Hi everyone, I'm Sam. I'm Joseph. Jazz. Victor. I'm Sharon.
Carrie.
Peter. I'm Ben.
Okay, Victor, you go by. Perfect. Yeah. And we will post a list of names at some point, just so that it's, a few of you who don't know everyone can at least see people's names written down, so it makes it easier, that's my guess.
Right?
Yeah.
Okay.
Okay. So almost all this stuff is on the web, and will be. And do you want to say a few things about what else you're doing in terms of,
Yeah. So there's all the slides will go on the website after the class, and then you've noticed there's a camera in the back, so a video of the lecture will go online as well, because there are some people that are going to take this remotely at McGill, so that's pretty interesting. The idea, though, is that we're not going to stand up here and talk for the whole time, because that's boring for you and for us. So we're going to try to do an activity pretty much every class, but we'll go over that in just a second with the syllabus. Techniques of geoscientific experimentation is kind of what we decided to call this, because it's broad enough to show that everybody needs to have some technical skill level, no matter what you do as an academic researcher. So today we'll go over kind of what we're going to do in the course and get the inventor's kits set up for everybody and do a little activity with that. So does everybody have their laptop, looks like? Yeah, okay, so we're good there. Ready to go? All right.
Yeah, fire away.
All right. So we'll go over to the class website in a second, but please take a look at the syllabus. And the lecture outline, at least that we think that we're going to do for every lecture, is up there until the end of the semester. So if you want to know what we're going to do, you can go look and say, that sounds really great, or no, we need more on something else. And take a look at the syllabus. We'll scroll through it really quickly. One thing I want to emphasize, though, our two course goals that we had there are to learn how to design and build basic mechanical and electrical devices for laboratory measurement work. So the design and build is bolded and underlined as is hands-on experience, because this is going to be a hands-on class. We're going to do things in class. We're going to take a field trip. We're going to do stuff in the lab. So you should be ready to do that. That's included in what we're going to do for grading. So there's going to be some exercises that are 40% of your grade. Those are kind of normal homework type things, or things that we do in class. A final project that we'll talk about is actually half your grade. So as you can imagine, that's building something, as again, hands-on. And then 10% participation for being here and doing things and being an active participant in the class. All right, the other thing is bring your inventor's kit and laptop to pretty much every class that we have. I will probably be using them most of the time. You can look online and see if we're going to be or not that particular time. But it's always handy to have around, because it's really easy for us to do some quick examples with this. And it's small enough that you can just leave it in your office and bring it down every time. And we'll go over the contents of that and get those distributed here in just a second, make sure everybody has one. The other thing is, since you all have your laptops, bookmark the course website so you can get to it now, because it's not a normal domain, it's a .tech domain. So it's not maybe the easiest thing to remember. but we'll show you what that looks like. All right. So we've got the syllabus, and the lecture outlines that I was talking about for the rest of the semester are down here. As you'll see as you go later in the semester, there's really not a class plan because things are going to change between now and then, most likely. The other big thing are, I've tried to put a lot of content that's helpful that maybe we don't necessarily cover in class on here. So say shop tools and practices, which is something we're going to be talking about this week. You can go into measurement tools, and there's a lot of information in here about, in this case, how to use these particular measurement devices. And there's videos embedded. If we go back, see machine tools. So there's a page for all kinds of machine tools that you're going to see when we go to the machine shop. And on those, lots of pictures, some text, and some videos as well. So it's worthwhile to spend some time exploring this. If you find something in here that is unclear, you can always just tell us, and I will try to correct it. Or there's this little Edit on GitHub button on every page. If you just click it, it takes you to, this is actually where the web page comes from. And you can go up here to Issues and say that you have a new issue with our content. And give it a title and tell me what's wrong, and I'll try to fix it. That's probably an easier way than telling me in the hallway, and I might or might not remember it. But of course, it's not required, just a handy way to interact. Okay, find the mouse. There we go. So, course website, everybody good with that? All right. The big thing in this class is the semester project. And so the idea is that we're all doing research, and you all have lots of problems that you encounter in your research where you probably have to build something to get past it, right? And the idea of this course is to let you do that. So it could be something that's electrical or mechanical, preferably something that would encompass a lot of the things we talk about, but not every problem needs that kind of solution, right? But you need to solve some kind of problem that either doesn't have a commercial solution or doesn't have an economical commercial solution. I'll show some examples of projects. If there's nothing directly related to your research, we can probably come up with something that would make everybody happy. Also, it can't cost thousands of dollars to build because we have very limited funding for doing this kind of thing. And it's nothing that's incredibly dangerous. So, kilovolts of electricity running into some kind of methane-containing pressure vessel is probably not a good semester project. But other than that, pretty much anything can go. So be thinking about that, and that's what a lot of the time outside of class is actually going to be spent on. We're going to try to minimize giving you things in class that you have to do outside other than just work on your project. Okay, so a few examples of, some of these are more research related, some of these are more fun type projects that you could do. So this is the underside of a Frisbee. And in here there's an Arduino, which is, it's just a smaller version of what's in your inventor's kit, an accelerometer that measures the acceleration out here in all three axes, an SD card to write the data to, and some batteries. So this, and that's actually a case where you can study the physics of Frisbee flight with about $25 in parts or so. So that's a relatively cheap and pretty fun project. That would be just fine. So that has some mechanical aspects, that has some electrical aspects, it also has some coding aspects to be able to pull data from the accelerometer and write it out to that SD card. This is one that folks in our lab are familiar with. Several people helped with it, including Carrie. This giant rock squeezometer and this little cube of granite, those are tweezers for scale. It's a hand-sized piece of granite. You could squeeze the granite. These strain gauges would measure how much you actually deform the granite, and it would show on this meter. So that's something that you could think about as maybe some kind of a demonstration project or something that would be good for doing outreach as well. And that's a relatively cheap project as well. Depends on how big scale you want to go with something like that. You can just compare sensors. So in this case, these are different kinds of precipitation sensors, a tipping bucket rain gauge and some kind of infrared rain gauge. And you could just say, I'm going to measure the same thing with different kinds of sensors and figure out what would be the best for what I do in the lab. So maybe DC-DTs to measure displacement. We'll talk about those later. Versus capacitive distance sensors. That's something that I'm doing right now for my research. That's just a simple instrument comparison. But it's really essential, actually. And so this is actually a picture of that. There's, way down here, there's a new type of sensor, a capacitive displacement sensor mounted, and this is a crude setup that lets us test that in the lab. So it doesn't have to be complicated in this big fancy thing that you get machined. You can hack existing hardware. So this is, if you go on Amazon, you can find controllers for little toy drones, cars, whatever. This is taking one of those controllers apart and wiring it into an Arduino to repurpose it as a cheap radio control system. So you could find something that you're interested in hacking apart and modify it. This one's pretty research related. This is a displacement sensor, and we actually needed to be able to hold it firmly and do some measurements in the lab. So these black pieces are 3D printed parts. They're designed in a free CAD. This entire thing can be printed and made for $5 to $10. And there's some magnets in the base, so it just sticks to whatever we want to measure. Something like that would be a really good example.
And there's awesome 3D printing capabilities at Penn State, incredible library. May or may not have already known about.
And hopefully everybody will get to print there. I'm hoping they aren't overloaded. I'm going to go check with them probably the week before we do that. But it's really nice. You can upload your 3D CAD file to their website, and they send you an email when it's ready, and you go to the library service desk and pick up your part. And right now it's free. It won't be always, but right now it is because it's a new service. Let's see a few more examples. This one falls in the category of a demo. Again, 3D printed parts in Arduino, in fact, the exact one that you have in your inventor's kit. And then these are rings of LEDs. And embedded somewhere way back here where you can't see, there's a magnetometer. And so this is a compass that shows you not only the direction, but the inclination of the Earth's magnetic field. And again, that's like $50 in parts. So you can do a lot with not a lot of money for these kind of projects. Let's see, I think there's a few more in here. There's a journal, Journal of the Physics Teacher, that they have a lot of really interesting things that you can get some inspiration from. Some of these were built from that. For example, these are infrared gates. So you can have them spaced apart and drop something, and it will start a timer when it goes through the first and stop a timer when it goes through the second. So you could have students do things like measure the value of gravity, whatever. Plans for a lot of this kind of stuff are available online and in that journal. You can also repurpose hardware if you don't necessarily want to hack it. This is a radar gun, and this is a radar gun in a trash can. Again, does not have to be elegant, outside measuring how fast snow falls, comparing it to rain. So you can do this pretty easily. And this is, you recognize a couple of them, I guess just Ben. Abby's gone right now. This is the classic spring slider demo that we use in earthquake mechanics. I think everybody in here has at least seen it, right? Right now, it's a pretty simple demo, right? You hook up the motor and you turn the motor on and it does its thing. What if you could add some sensors to this? Maybe add a displacement sensor or add a load cell out here so that you could have a real-time graph showing people of what the stress is on this thing. So you can think of just taking a classical demo and modifying it and adding instruments to it. That's another way to think about these projects. And there are sources of information literally everywhere. I have in my bag, and I'll set them out if people want to look at them, a couple of these magazines, but they're at Barnes & Noble. You can find them online. Servo is a robotics magazine. Nuts and Bolts is more of a pure electronics magazine. There's a lot of machining magazines, the Home Shop Machinist being the most popular, that you can flip through and go to their websites and get a lot of ideas. And there's also websites like Hackaday, where there's probably about a dozen new, pretty incredible projects every day. And then YouTube and Make Magazine all have pretty incredible sites as well. In fact, on Hackaday, you can go, there's a project that was done by somebody about this level. I would consider this an advanced project for this class, though, where they took these little, cheap USB dongles that can be used to receive radio signals like TV, so you could plug it into your computer and watch TV. And they took 2 of those and were able to make a passive radar that could track airplanes by the UHF bounce off the airplanes. So there's crazy stuff out there that people do. We're going to do an activity today, but first we need to get everybody with an inventor's kit. So you should have either $95 cash or check with you, and then we'll go around. So who needs a kit?
While we're thinking about that, let's just take a second to see, what else did you think we were going to hear at this stage that you haven't heard yet? Anybody have questions about the structure of the course, or about what we might cover, or about